Well, hi everyone. In this video, I'd like to do a few examples related to the question that I've got on my board here. How can we decide, yes or no, whether a set of vectors that is given to us forms a spanning set for whatever our vector space is? That's a good question. Yes or no, if I take a set of vectors, do they form a spanning set for the large universe vector space that we're looking at? Here is an example that I've written notes down before, and I want to just review it really quickly. I've given you three vectors in R3, namely 1, 1, 3, 2, -1, 4, and 3, -3, 5. And I would like to ask whether those three vectors form a spanning set for R3. Now, the way this works is if they're going to form a spanning set for R3, that means that every single arbitrary vector in R3, I'm going to call it XYZ, every single vector in R3, a random arbitrary vector, must be expressible as a linear combination of the vectors in our set. So I've written that here on the right-hand side, C1 times the first vector plus C2 times the second vector plus C3 times the third vector. And I'm going to try to see, notice I put the word try over that equal sign. It's because I don't know if I'm going to be able to make this work or not, but I'm going to try to take an arbitrary vector with general letters X, Y, and Z and write it in this form. Or at least I want to know that I can write it in this form. Yes or no? Okay, well, as you can see, there are three slots to our vectors. And if we focus one at a time on the left slot, the middle slot, and the right slot, I can make equations that match the left side to the right side. Notice that the X, the Y, and the Z are going to be equal to some expressions involving the C1, the C2, and the C3. Which, by the way, the C1, the C2, and the C3 are the unknowns in this system. Those are what we are trying to see whether we could solve for or not. So we can take this system of equations and we can just put it into an augmented matrix. Notice that the X, Y, and Z forms the augmented column over here. The unknowns in the system are C1, C2, and C3. And what I really want you to notice is that when we move this system of equations into the matrix, the original vectors show up in the columns of this matrix. So that is actually always going to happen on any example of this nature. And so for that reason, we actually can sort of take this part of it, which I'm going to circle. We can take this part of it and just kind of bypass it. We don't really need to write all of this out because we already know what's going to end up happening, which is that the original vectors are going to fill up the columns on the left side of my bar, and my arbitrary vector is going to fill up the entries of that vector, I should say, are going to fill up that far right column. Now, the next step, as you could imagine, would be to try, I use that word try again, to try to solve this system. Not every system can be solved. As we know, systems can be inconsistent. And in fact, if we do the EROs here, which I'm going to omit the details of because it's not really the main point of what I want to talk about now, this is the row echelon form that you would come up with. And you can see that the first row didn't really change at all, but the second and third rows, they underwent quite a variation after doing those elementary row operations. And most importantly, what you'll notice is that on the bottom row of this matrix here, I ended up getting a 0 and then a 0 and then a 0 on the left side of that bar, which means that the pivot that goes in the bottom row actually shows up in the far right column over here. Now, it's not specifically a 1, but you can see that for a lot of values of X, Y, and Z, this pivoted lower right corner is not 0. Now, guys, it is true that for some values of x, y, and z, you could make this bottom right corner turn into a 0. After all, this is an equation of a plane, actually, and that plane could be equal to 0. So you see in the numerator here, I have negative 4x minus 2y plus 3z, and that if that was equal to 0, we would actually have no pivot in the far right column in this example. What does that mean? Well, that actually tells us that these three original vectors that we started with, they are capable of spanning some vectors in R3. Namely, it will be possible for those three vectors to span any point x, y, z that satisfies this equation. So some of the points in R3 can be expressed in terms of our original vectors. That makes sense. But the problem is we cannot express all vectors in R3 using these three vectors, because for most choices of x, y, and z, this lower right corner is a pivot, and when you have a pivot in that far right column, guys, we know what that means. It's not consistent. There is no solution to the system for the unknowns C1, C2, and C3. So the answer to this question is no. In general, no. We cannot span R3 using the three vectors that were given. Now, what you might have noticed, actually, something kind of interesting here, is that when we set up this matrix by putting the vectors into the columns, the matrix of coefficients here on the left side is actually a square matrix. And even by the time we've done EROs on it, we have this square coefficient matrix that ended up with a row of zeros on the bottom. That actually tells you something about the matrix, doesn't it? It tells you that this matrix was not invertible, and also that its determinant is 0. Keep in mind, guys, if the determinant of this matrix is 0, which it is, right, then all of the other matrices that we obtained along the way that were involved in the EROs that gave us that matrix of determinant 0 would have had determinant 0 as well. In fact, this matrix has a determinant of 0. Well, what does that actually mean? One of our applications of determinants, which I mentioned, is that the determinant of a 3x3 matrix measures the volume of a parallelepiped, right? A parallelepiped determined by either the rows or the columns of the matrix. Well, this parallelepiped has a volume of 0 because the determinant of this matrix is equal to 0, which really means that the determinant of this matrix is also 0. That means there's no volume. And that means that these three vectors all lie in a single plane. If they don't create any three-dimensional volume, then those three vectors must be all laying flat within a single plane. And actually, believe it or not, I can tell you what plane it is. It's actually this plane right here. This is the one. This is the plane that will have all three of these vectors in it. And these three vectors, being that they are in that plane, they can span that plane. They can be a spanning set, not for R3, but they can be a spanning set for that plane. So I want to give you a quick general principle here about how this determinant could be used in a more general situation. So a general principle, let's just add this to our repertoire of tools that we can use, okay? It just says this: if we are given n vectors, let's say v1, v2, and ... up to vn, that are in Rn, which, by the way, is what we had here. We had three vectors in R3 for this example. But in general, if we have n vectors in Rn, then what I'm going to say is that that set of vectors, v1, v2, and dot, 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 up to vn, is a spanning set for Rn. Those n vectors, they are a spanning set for Rn if and only if the determinant of the matrix that we obtain by building those vectors into the columns of an n by n matrix, as long as that determinant is not equal to 0. So here's a little application of determinants that's pretty handy to know. Okay? So if the coefficient matrix is a square matrix, like 3 vectors in R3 being arranged into the columns of that matrix, that's what we did here. If we take the determinant of this matrix, and if we get 0, which we will on this example, then that's bad. That means no, my vectors do not form a spanning set for Rn. But if the determinant is not 0, what would that have meant, right? What that would have meant is that your pivots, if we think about a matrix whose determinant is not 0, that's an invertible matrix. An invertible matrix would have full rank. It would have had a pivot even down in this bottom corner on the left side of the bar. It would have been, the pivots for invertible matrices always trail right down the main diagonal. And if the pivot was there, then it wouldn't have been over there. And I would have had a consistent system, you see. That is the point I'm trying to make. So we can actually boil this question of how to decide whether a set of vectors forms a spanning set for V down to a question about determinants in some cases. Now, we can't do that in all cases, because it isn't always going to be the case. It is not always going to be the case that we end up with a square matrix here, okay? So the real test that we should write down, the real answer to this question, the best answer to this question that I can give you, right? Let's come back to this question. Is what we do is we lay our vectors into the columns of a matrix. I'm going to use bars to kind of separate these columns. And I'm going to augment this matrix with number symbols. Remember, I don't really care what's going on in that far right column. It has X's, Y's, and Z's in it. But the exact expressions will change as I do the EROs. But I don't really care so much. But if a pivot ends up over here in this far right column, then my system is not consistent and it's not a spanning set. So basically, there's 2 outcomes here that I want to explain. That this is either a yes, that it is a spanning set if consistent, and it would be no if inconsistent. This is really the catch-all way of answering the question on the board here. This determinants idea that I gave you a moment ago works great if the matrix has a square size. But not all matrices are square, including these matrices that we have here. I'm going to show you an example of that. The point being that what we really need to do is hit this matrix with EROs and figure out whether it's consistent or inconsistent. That's what really matters. So with that in mind, I want to do another example. Let's do this one. Is the set 1, 1, 1 and 2, 2, 2 and 3, 3, 3 and 4, 4, 4, I'm going to take 4 vectors this time. Is that a spanning set for R3? Is that a spanning set for R3? This time, I'm gonna do the shortcut way. I am just gonna solve this the way that I hope you guys will try to solve problems of this nature as well, is it's gonna streamline the process nicely, right? So you see what I've explained here, we lay these vectors into the columns of this matrix. So the first vector is 1, 1, 1. The second vector is 2, 2, 2. The third vector is 3, 3, 3. The fourth vector is 4, 4, 4, right? Just laying them vertically in the columns, and I'm going to augment that matrix. Now, previously I augmented this matrix with X, Y, and Z, but I realized after doing that first example that I don't really care about keeping track of the alphabet soup of X's, Y's, and Z's as I do EROs. So I am just going to fill in number symbols there. But what we have to understand, guys, is that these number symbols always just remain number symbols. They really are changing when I do these EROs, but they're not becoming zero or non-zero as a result of an ERO. They are going to continue to involve the letters that you would have used for your arbitrary vector here, like X, Y, and Z. So we're just going to keep those number symbols going. Now, what you might notice here, guys, if I leave the first row the same, I want to think about EROs here. You might notice that if I take the negative of the first row and I add it to the second row, I'm going to get 0, 0, 0, 0. And then, guys, the negative of the first row added to the second row on the far right is really still just some other number symbol. Okay, remember, it's not, you're not subtracting two number symbols and getting 0. This is like really an X and a Y, and you're subtracting X from Y, and that does not give you 0. That gives you the difference of the two variables. The point is, this is not 0 right here. Okay, so I'm not even going to finish this matrix. I already know that we do not have a consistent system, right? So I would normally be looking for solutions for the unknowns. The unknowns are here, lined up with these columns, C1, C2, C3, and C4. But as you can see, it's not going to have any solutions. So this is inconsistent, and if we have an inconsistent system, meaning there's a pivot over there in the far right column, we're going to say no is our answer. Okay? Actually, this probably should have kind of made sense. I mean, the vector 1, 1, 1 goes like that, and then 2, 2, 2 is just twice as long, and 3, 3, 3 is 3 times as long. 4, 4, 4 looks like that. Guys, all 4 of these vectors are pointing in the same single direction. And so when you think about linear combinations of them, you're never going to be able to sort of get off of this line. The span of these 4 vectors is actually just going to be that one-dimensional line. And that's quite a small chunk of R3. So these vectors are not going to be a spanning set for R3 by a long shot. Okay, let me do one more example. Feel free to pause this video if you're having any questions and want to just watch this at a little slower pace. But let me just try to give you one more example that involves a different vector space. Okay, so let's do this one. Here's my example. Is the set of 1, 2 plus 3x, 4 plus 5x plus 6x squared, 7 plus 8x plus 9x squared plus x cubed. Is that a spanning set for P3 of R? So I'm working this time with polynomials. I just want to see how this all plays out if I actually have a polynomial example instead of just vectors with slots. Well, the truth of the matter is, you're going to end up with the same kind of a setup here. If I start off, okay, let's say I start off by trying to take a random cubic polynomial here. I guess I'll write it like this, guys. a plus bx plus cx squared plus dx cubed. If I try, okay, I'm going back to the way I set this up in the first place. If I try to write that as a linear combination, let's say c1 times the first vector, which is 1, plus c2 times the second vector, which is 2 plus 3x, plus c3 times 4 plus 5x plus 6x squared, and finally plus c4 times the vector 7 plus 8x plus 9x squared plus x cubed. If I take all of that and I set it equal to 0, I'm sorry, I'm not setting it equal to 0. I'm setting it equal to my arbitrary vector here. This is my arbitrary vector. Right, this time I don't have slots. I don't have like a left slot and a middle slot and a right slot. But I do have the different powers of x that I can kind of match up from the left to the right. So like if I look at the constant term, if I just look at the constant term on both sides of my equation, on the left I have an a, and what do I have on the right? Well, I'm going to underline everything that is basically a constant. The constants just don't involve the x's at all. So I would have a c1, a 2c2, a 4c3, and then plus 7c4. That's the constant term. And then I have the x term on the left and on the right. On the left, the x term has a b on it. And on the right, if I just focus on the x terms, here's an x term, here's an x term, and here's an x term. So let's write those down. 3c2 plus 5c3 plus 8c4, right? And then the x squared term, well, on the left side, there's a c in front of that x squared. And on the right side, there is a 6c3 and a 9c4. Okay? And finally, the x cubed terms. So instead of 4 slots, I have 4 different powers of x. I have the constant term, the x squared term, and the x cubed term. On the left side, the x cubed term is right here, dx cubed. And on the right side, the only place that I have an x cubed is way over here at the end with a c4 in front of it. So dx cubed should equal c4 x cubed. And that means that the d and the c4 should match. Okay? So we do again get a system of equations. And so we do again have the possibility of just laying out these equations as an augmented matrix. And so it, in that sense, looks a lot like the example that I did earlier with R3. It's going to look something like this, and 0, 0, 0, 1, and D. Okay? Again, I want to point out that we really didn't need to do all of this setup here. We could have taken these 4 polynomials that we were given and lay them directly into the matrix. You see this polynomial 1 here? You can think of that as 1 plus 0x plus 0x squared plus 0x cubed. And it just fits into that first column. The second vector, which is 2 plus 3x, well, that fills up the second column of this matrix. 2 plus 3x plus nothing x squared and nothing x cubed. And then the third polynomial, which is 4 plus 5x plus 6x squared, fills up the third column here. The 4, 5, and 6 are showing you that. And then the 7, 8, 9, and 1 are filling up the fourth column. So this idea of just going straight to the matrix and laying your vectors vertically into the columns of this matrix that you're setting up is valid and still good no matter what kind of vectors you have. It doesn't just have to be for vectors in Rn. Really, even in this polynomial context, we can take the given vectors and just lay them into the columns of this matrix. Now, I'm not even gonna do any EROs here because I pretty much have the positions of the pivots already figured out. And look at that. They go all the way right down the diagonal of this matrix. And the most important thing is there is no pivot in the far right column. That means that this is consistent. It is consistent. And that means, yes, these four polynomials do form a spanning set for P3 of R. It's not the only spanning set, by the way. Of course, we've seen earlier that just these basic polynomials right here, 1x, x squared, and x cubed, that forms a perfectly nice spanning set for P3 of R. But now we see a different spanning set for P3 of R, which is also valid. Okay? So just in summary, guys, what have I been trying to explain in this video? If I give you a set of vectors and I want to decide whether they form a spanning set for V, what am I going to do? I'm going to lay the vectors into the columns of a matrix. I'm going to augment that matrix with a general vector, but of course I should have also pointed out here that I could have just as well been happy enough to put number symbols over here, right? I don't really care how the EROs change what's over there. But we're going to augment this matrix like so. We're going to do the EROs and just decide whether it's consistent or inconsistent. If it's consistent, then the vectors I started with, they are a spanning set for V. If it's inconsistent, then no, the vectors do not form a spanning set for the vector space. And in the case when your matrix has a square size, we could have done that with this matrix, for example, as well. If the coefficient matrix is a square size, you can use the determinant. You can use that determinant to decide whether or not this is going to be a consistent or an inconsistent system. That's really not a new idea for us. We've known that for a while. When you have an invertible coefficient matrix, right, you will be able to solve the system. Okay, whereas if the matrix is not invertible, that's usually a bad thing. And in that case, in this setup here, we're not going to be able